At the end of this video, I hope that you can describe the electron C model of metallic bonding and explain why metals are good electrical conductors, explain why metal surfaces are shiny, and explain why metals are malleable and ductile, but ionic crystalline compounds are not. Chapter 6, Section 4, Metallic Bonding. Chemical bonding is different in metals than it is in ionic, molecular, or covalent network compounds. This difference is reflected in the fact that metal has several unique properties. They are excellent electrical conductors in the solid state, much better conductors than even molten ionic compounds. This property is due to the highly mobile valence electrons of the atoms that make up the metal. Such mobility is not possible in molecular compounds, in which valence electrons are localized to each electron pair bond between neutral atoms. Nor is it possible in a solid ionic compound in which electrons are bound to an individual ion and is held in place in a crystal structure. The metallic bond model. The highest energy levels of most metal atoms are occupied by very few electrons. In S-block metals, for example, 1 or 2 valence electrons occupy the outermost orbital, whereas all 3 outermost p orbitals, which can hold a total of 6 electrons, are completely vacant. In addition to completely vacant outer p orbitals, D-block metals also possess many vacant d orbitals in the energy level just below their highest energy level. Within a metal, the vacant orbitals in an atom's outer energy levels overlap. This overlapping of orbitals allows the outer electrons of the atoms to roam freely throughout the entire metal. The electrons are said to be delocalized, which means that they do not belong to any one atom, but move freely about the metal's network of empty atomic orbitals. These mobile electrons form a sea of electrons around the metal atoms, which are packed together in a crystal lattice, as is seen in figure 6-18 or on the screen now. This model shows a portion of the crystal structure of solid sodium. The atoms are arranged so that each sodium atom is surrounded by 8 other sodium atoms. The atoms are relatively fixed in position, while electrons are free to move throughout the crystal, forming an electron sea. The chemical bonding that results from the attraction between metal atoms and that surrounding sea of electrons is called metallic bonding. Metallic properties. The freedom of motion of electrons in a network of metal atoms accounts for the high electrical and thermal conductivity characteristics of all metals. In addition, because they contain many orbitals separated by extremely small energy differences, metals can absorb a wide range of light frequencies. This absorption of light results in the excitation of the metal atom's electrons to higher energy levels. The electrons immediately fall back down to lower levels, emitting energy in the form of light. This de-excitation is responsible for the shiny appearance of metal surfaces. Though most metals are easy to form into desired shapes. These two important properties are related to the characteristics malleability and ductility. Malleability is the ability of a substance to be hammered or beaten into thin sheets. Ductility is the ability of a substance to be drawn, pulled, or extruded through a small opening to produce a wire. The malleability and ductility of metals is possible because metallic bonding is the same in all directions throughout the solid. One plane of atoms in a metal can slide past one another without encountering any resistance or breaking any bonds. By contrast, recall from section 6-3 that shifting the layers of an ionic crystal causes the bonds to break and the crystal to shatter. Metallic bond strength. Metallic bond strength varies with the nuclear charge of the metal atoms and the number of electrons in the metal's electron sea. Both of these factors are reflected in a metal's heat of vaporization. When a metal is vaporized, the bonded atoms in the normal, which is usually the solid state, are converted into individual atoms in the gaseous state. The amount of heat required to vaporize the metal is a measure of the strength of the bonds that hold the metal together. Some heats of vaporization for metals are given in Table 6-4 on page 182 of your text or on the screen now. At this point, I hope that you can describe the electron C model of metallic bonding and explain why metals are good electrical conductors, explain why metal surfaces are shiny, and explain why metals are malleable and ductile, but ionic crystalline compounds are not.